Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering at the University of Calgary. And this is the intro video for Lab 1 in ENCM369. And in this video, I'm only going to go through part A just to get you started on the lab. And it's a bit of a longer video, and I don't want to kind of intimidate you and give you the impression that these labs are gonna take forever. But I do in this video go through a lot of stuff very carefully, very slowly. I do a lot of talking just because I think it's important to there's a lot of sort of skills and things to keep in mind in order to succeed in the labs in 369. And the labs are a big part of this class. The hands-on component is really, really important. So, if you've got some experience with hobby electronics, if you've used breadboards before, stuff like that, you might want to double speed me through some of this video, but I think it's important that everybody understand and is very comfortable with all of the concepts that I talk about in this video. Like I said, in order to set you up for success for the rest of Lab 1 and for the remaining labs in the class. Okay, so what I'm going to do with the rest of this video is give you a head start kind of introduction to Lab 1 and just kind of cover over some of the basic things that you need to get started. So the first thing I'm showing here is my desktop, and I've got basically, I guess, 4 things open on this desktop, and you can see it a little bit better if I sort of separate it out like this. So the first thing I have open is the AVR datasheet in all 660 pages of its full glory. Like I said, this is an invaluable reference. There's no way you can do these labs without having this open basically the entire time. And like I said, you don't have to read the full 660 pages. I will let you know what you need to look at. Although certainly as you start to think about using the AVR for your ENEL 300 design project, you're going to have to start to get familiar with other parts of the datasheet as well. The second thing I've got open is my handy dandy Lab 1 handout. And if we look at the first page, a little bit of an introductory statement, stop, make sure you're watching this video. So if you're watching the video, you're okay. Here's the pre-reading section. So I tell you which sections of the datasheet to read. There's a table of contents that I think starts on page 7 or 6. Yeah. So the table of contents starts on page 6. It's hyperlinked, so you can click on things and click back, so it's easy to navigate. This first lab is going to deal with digital I/O. So section 18 is really important. So we're going to skip over, all of these other sections. Section 18, and then there's reading in here, and I give you the specific section numbers. So here's a little section on some common programming errors. You can kind of skip over this for now. Just know that it's here, just in case you get one of these errors, and there's a little bit of solution help. And then we move on to part A. And so part A is basically what I'm going to be working through in this video. I'm essentially going to show you how to do part A. And the other 2 important things that I've got open are the MP Lab discussion environment. And so before this video, I'm assuming that you have gone to D2L, downloaded the little instruction PDF for installing the MP Lab test environment or development environment, and you've tested it and it's working okay. If you haven't installed it, stop the video now. Download that document, install it. If you have any problems or questions, post on the discussion forum. The final thing I've got open is Scopy. So we're going to be using Scopy in this first part to connect to, mainly as a multimeter to test voltage levels. And so I'm going to connect to Scopy. and it has fired up, and it is the voltmeter. There we go. It's the voltmeter functionality that we're going to be using. And so, yeah, make sure you've got all 4 of these things open on your desktop and ready to go. The first part of part A is basically connecting your power. Now, you'll see I've got a breadboard here that'll be similar, not identical, but similar to the ones that you'll be working with. And I've got my the end of my 5-volt wall wart power adapter. And then I've got my little connector for plugging into my power adapter. Your connector is going to look different. You won't have exactly this one, but it's basically the same idea. You'll notice that I've used zip ties to fasten down my connector. Again, you can use tape or an elastic band or something like that. Although zip ties, you can get big bags for not very much of them at Home Depot and stuff like that. They're handy to have around. And the wall wart plugs into there. And my particular adapter has wires coming out of it. Yours might plug directly into the breadboard, but it's the same idea. But basically, my plus voltage is coming out of this red wire, and I've plugged it into this trace on my breadboard. And my minus, or my ground basically, runs out of this black wire, and I've plugged it into this trace. Now you'll see on my computer screen that I've fired up Scopy and I've fired up the voltage, the voltmeter. And so I'm going to plug in the positive lead there in my breadboard and the negative lead there in my breadboard. And you have to click run on Scopy for it to do any kind of measurement. And you can see that on channel 1, we're measuring 5 volts now. So just a reminder about how these breadboards work. Maybe you've got experience, maybe you don't. But just a reminder that in this part of the breadboard, these traces run horizontally. So that means this is where, and I'll bring it a little closer to the camera so that you can see it. So this is where my plus 5 volts is connected. That means that this square, this square, this square, and this square is all connected to plus 5. The other rows are not connected. So if I move my voltmeter, if I unplug it and I plug it in the row just below it, you'll see that I'm reading 0 volts. It's only when I plug into one of these horizontal traces that I get my 5 volts. And the same thing over here. This horizontal row is connected to 0 volts, but this one is not. Now, the exception is these traces on the outside. These traces are meant for power and ground, and they run vertically. So what I want to do is I want to plug my plus 5 volt power supply into these 2 traces so I have access to plus 5 volts and ground all the way down my my breadboard. So what I'm going to do is I'm going to unplug my voltmeter for now, and I've made these connector wires. I like to use color coding. I think that this is good practice, especially if you're cutting your wires. Some of you might be used to using one of these wiring kits, right, that have pre-cut and pre-stripped wires. If you have one of these kits, then you kind of just use whatever color wire is the right length. But if you're cutting your wires yourself from something like this, where you can choose your color, choose the colors that make sense for you. So I'm going to use red for plus 5 volts, and I'm going to use black for ground. And what I'm going to do is I've cut some wires, and I'm going to take, I'm going to choose the left-hand trace here, and the left-hand trace here to be plus 5. And so I'm going to take plus 5, and I'm going to connect it to my trace over there, and I'm going to take +5 and I'm going to connect it to my vertical trace here. I know my hands are in the way. I'll move them in a second. And then I'm going to use the black wire to connect ground. And then I'm going to use my black wire over here to connect ground as well. Okay, so now I'm going to take my hands away and you can see, you know, how I've connected things. So I've taken this black wire and I've connected it to the left hand, or sorry, to the right hand vertical trace. I've taken this black wire and I've connected it over here to the right hand vertical trace. Here I've taken the red wire and I've connected it to the left hand vertical trace, and this wire connects over here to this left hand vertical trace. Now, whenever you make a power connection, it's super important that you use your voltmeter to test to make sure that you haven't hooked anything up backwards. Because if you hook up power backwards, that's a great way to burn out your chip and wreck your chip, right? So these microcontrollers are tough, but they're not that tough. So what I'm going to do is I'm going to take the minus for my voltmeter, plug it into the left-hand trace, and I'm going to take the plus and plug the minus into the right-hand trace, and the plus into the left-hand trace, and we can see that we've got 5 volts. Same thing over here. Again, we have 5 volts. And I can take this anywhere. I can plug it anywhere along this vertical trace. And I will measure +5 volts. Over here, I can plug this anywhere along my vertical trace and I'll get +5 volts, except if I go there. This particular breadboard, they're not all like this, but this particular one, halfway through, will cut these vertical traces off. So the vertical traces won't go past the midway. And so what you're going to have to do is what I'm going to have to do is I'm going to have to jumper my 5 volts down and jumper my ground down. And same here, jumper 5 volts down and jumper ground down. The reason why some boards do this is just so you could have 5 volts up here and 12 volts down there if that was important for your circuit. But I'm just going to add jumpers here so I've got the 5 volts and ground all the way down my board. Okay, so now you can see that I've added my power jumpers, and you know, I can test with my multimeter to verify that you know, I now do indeed have 5 volts worth of power on across my power rails on both this side of my breadboard and that side of my breadboard. And so the next step is to put our microcontroller onto the breadboard. Now, a couple of things to be aware of. First of all, it is possible to destroy integrated circuits, any integrated circuit, with static electricity. So I used to work in an electronics manufacturing facility, and making sure that static electricity was discharged was a big deal, especially on the factory floor. We would wear special shoes that had grounding strips, and then the floors would be covered with special wax that would allow our shoes to ground our bodies when we walked out onto the factory floor. And when we sat down to work with electronics, we would always wear wrist straps that would constantly ground ourselves when we were touching like open chips, like I'm about to do now. We don't have grounding straps for these labs. The AVR MCU is pretty tough, but what you should do is make sure that you touch something metal, something that would be grounded before you touch these touch the leads on your chip. So, you know, like the casing on a power supply, or you know, the cover of an appliance or something that you're close to that would be connected to ground. And so I've done that. And now what I'm going to do is I'm going to put my microcontroller chip across the gap in my breadboard. It doesn't really matter where on the breadboard you do it. I'm just going to sort of do it down here. Now, when you get these chips brand new, I've already used this chip in a breadboard, but the little feet are going to be a little wider than the breadboard, so they'll be sort of pointed. Whoops. Make sure I get that in there. These feet will be sort of pointed out a little bit, and so I had to just sort of use my fingers to squeeze them in a little bit before they would be or before they were able to fit onto the breadboard. And so I've done that, and I'm just going to press this chip into the breadboard. Make sure you press it nice and firmly, because if you just kind of weakly put it in, it's not going to make contact with all of the pins, and that's going to cause you lots of problems when you troubleshoot. Note also that the microcontroller, I don't know how well you can see it in this video. There, that's not too bad. The microcontroller has a little bump at the top of one end, and that bump should always face to the top of your circuit. That is how you're going to know where pin 1 is, because when we go back to our data sheet, I believe it's on page 17. Oh, almost. Page 14. This is the pinout diagram for our chip. So here's all 28 pins, and you'll notice up here that pin 1 is represented as being close to this little dot. This little dot basically represents the bump at the top of the microcontroller. So that means that this pin is pin 1, 2, 3, all the way down to pin 13, 14, 15 is here, 16, you know, all the way up to, you know, pin 27 and 28. Okay, so the next step in the lab is to connect power and ground. And so there are 2 ground pins that need to be connected to my ground rail. And you can see where those are on our pinout. Here's the first ground pin, and here's the second ground pin. So the first ground pin is the one right down here, and then the second ground pin is up here somewhere. There's also 3 different connections where we have to connect our +5 volts. The AVDD pin, VDD IO2 pin, and VDD. And so we can see that pin is pin 6, pin 14, and pin 20. So I'm going to do that now. Okay, so I've hooked up my power. Now, one thing I should mention before you hook up your power, make sure your power is disconnected, right? Because if you hook up 5 volts to the wrong pin, it's possible you might damage your circuit. And so you can see that I have connected all of my my power connections here. I've kept my red and black color scheme, red for +5 volts and black for ground. Again, it just helps keep the board neat and makes it easier to troubleshoot. So before I hook my power back up, I'm going to make sure I've connected everything to the proper pin. So looking at my 14 or my 28 pin out diagram in the data sheet, I can see that VDD IO2 is pin 6. So 1, 2, 3, 4, 5, 6. I've got that connected with a red wire to +5. Down here, A VDD is easy, it's just the last pin. So the final pin on the left-hand side, again, red wire connected to plus 5 volts. On the right-hand side, pin 15, also pretty easy. It's the first pin on the right-hand side, so black wire connected to ground. Up here, VDD is pin 20, so I'm going to count that up. 15, 16, 17, 18, 19, 20, connected with a red wire to plus 5. And the final ground connection is a black, just above VDD, and it's a black wire connected to ground. So I am ready to power my circuit up. So even though I have carefully counted out all of my pins, it's important that I also use my voltmeter to just make sure I've got plus 5 volts wherever I need it. So I'm going to plug the minus lead into ground, and then I'm literally just going to touch each of the pins on the MCU chip to make sure I've got plus 5 volts. So here I have plus 5, down here I have plus 5, and over here also plus 5. And this is where, you know, my color scheme is making it handy for me, right? Because I know that you know, everywhere there's a red wire, I should have plus 5. If it's a black wire, I should have ground. And of course, when I touch the wire there, it still reads 0 volts. And so I'm comfortable that, my power is connected correctly, and I can proceed to the next step. Okay, so now we're ready to hook up the programmer. So this is what the Snap programmer looks like. And there's basically 3 connections coming off of the Snap that we care about. Now, I'm not sure you can see how well you can see it in the video, but basically right here on the connector, or on the printed circuit board beside the connector, there's a little black triangle. That means that that black triangle is next to pin 1. And so on my diagram in the lab handout, the Snap pinout diagram, you can see pin 1 is MCLR, pin 2 is VDD, 3 is ground, 4 is PGD, and so on. Now, you basically only have to connect 3 wires from the Snap to your board in order to load programs into the AVR. The first 2 are VDD and ground. And so pin 2 is VDD, and so I've got this red wire to indicate VDD, and pin 3 is ground, so I indicate that by my black wire. And you connect ground into the ground on the breadboard, and VDD into plus 5 volts on the breadboard. The purpose of these 2 connections is basically to allow the Snap programmer to sense whether or not there's power supplied to your circuit. If you don't plug these in, you'll get a little error in MPLAB saying that you haven't, there's not proper power levels supplied to the board. Now this last wire, this blue wire, is plugged into the UPDI pin on the AVR. So all of the programming that happens is done using just a single chip, the UPDI chip, on the microcontroller, which is really nice. And the UPDI chip is right under VDD, and so we just plug that right underneath VDD on the breadboard. So now there's one extra step that we have to do in order to get the programmer to work. There's a little bit of a bug basically on the Snap programming board, such that the pull-up resistor is not good enough on the board. And the pull-up resistor is basically a little resistor that's connected to plus 5 volts or whatever VDD is. And when no current is flowing, that resistor basically allows the pin to float up to plus 5 volts. Now we have to add a separate pull-up resistor, and I've played around with this a little bit, and 1.2 kilo ohms works pretty well. So here's my 1.2 kilo ohm resistor. Now, if you pull the resistor just out of the equipment drawers, they're all going to have these nice long leads on them. I like to trim my resistors down. So again, it makes your circuit a lot neater. So I'm just going to trim these leads. And don't worry about trimming them, because basically your resistor is not going to be reused. We don't sort of put the resistors back into the drawers when you're done with them, kind of thing. And so the resistor needs to go between the UPDI pin and plus 5 volts. And so that's what I've done there. And now we're ready to program. So this concludes all of the hardware connections for part A. And now we're just the last part of part A is just making sure we can actually load a program into the AVR chip. Okay, so the last part of part A is basically verifying that the MPLAB environment can load a program via the Snap programmer into your AVR chip. And so I'm assuming that you have already worked through the development environment setup document, and you've gone all the way to the end, right? Because all the way to the end is where you test compile, you create a project and you test compile a program. And if you haven't done that, stop the video, make sure you do that. So assuming you've done that, we're going to create a project just like we created a project inside to test the development environment. So we go to New Project, Microchip Embedded Standalone. So these defaults are fine. Click Next. Now we're going to choose the AVR 128 DB28 device. And under Tool, instead of Simulator, we're going to select the Snap Programmer. Now, this Snap Programmer is only going to show up if you've got the Snap Programmer plugged into the USB port on your computer. If it doesn't show up, then either the Snap Programmer is bad or your cable might be bad. And it's surprising how many micro USB cables are bad. I've actually thrown away 4 of them doing this this year, just sort of. And I think it's maybe because some of these cables we get with like cell phones and stuff like that, and they're meant to charge but not actually support communication. So if you've maybe got a cable that is just for charging a device but not for communicating with the device, that might be something that you might want to check. So clicking Next, I've got 2 versions of the compiler installed here just because this is from last year. I'm going to choose the more recent one, 2.4. Click Next. The project name, I tell you that you should call it Lab 1 Level Switch. I'm just going to call mine Winter 2023 Video Demo, because it's the Winter 2023 semester right now. And click Finish. So this creates in a little entry in my projects window. You'll notice I've got a bunch of other projects in here because I've been working on a bunch of other stuff. And so inside source files, right click and click on new AVR main.c. You can call this AVR main. You can keep this default or you can call it Lab 1. It doesn't really matter. Click Finish, and this opens up. Now, what I want you to do is I want you to replace the code here with the level switch.c file that I've posted on D2L. So I've got level switch opened here, and so I'm basically just going to take this code, I'm going to cut, and I'm going to paste it into the middle here, and I'm going to click Save. Now, Before I test the compiler, I want to take a look at what this code actually does. So the first line enables port PA5 as an output pin. Okay, so which one is PA5? Well, if we go back to our pinout, PA5 is the second pin from the top. And how do I configure that as an output pin? I copy the value, the binary value 0010, 000, into this funny variable name called port_a.dirset. Okay, well, how did I know how to do that? Well, if you've done the pre-reading for the lab, this might ring a bit of a bell. So let's go to the data sheet and go down, or up, I guess, to the table of contents. And one of the things that I've asked you to read is section 18. Well, section 18 talks about where we, or how we configure ports for digital I/O, creating digital outputs and reading in digital inputs. And so there's a bunch of sections here, but there's also these register summary sections that you'll have taken a look at. And sure enough, dirset is actually the name of a special function register. And if we click on dirset, we get a little description here, and it says writing a 1-bit will set the corresponding bit in our port as an output pin and enable the output driver. So basically, each one of these bits in this register correspond to a different pin on either port A, port B, port C. Yeah, and there's just port C on this chip. There's no port D. So here in the development environment, we start with the variable called port A. Now, port A is, as the name suggests, this is related to port A on the AVR. And if I type in port A in the development environment and I hit dot, then I get a whole listing of different things that will follow the dot. And all of these things correspond to all of the special function registers in this listing. So there's dir, there's dirset, there's port control, there's pin config. A lot of these we don't use, but you'll see we get this listing. And so basically we choose the special function register that we want, in this case dirset, and then I can write in whatever binary value I want. And so if I want to write in a binary number and I just want to specify it in ones and zeros, I type in 0b, and then on dirset, I can write in a 1 to any one of these pins that I want to set as an output. So this would be PA7, which this would be PA6, this would be PA5, and so on. We only want to set pin 5 as an output, and that's why only this third bit is set. The dir CLR special function register is the one we use to designate an input pin. So I want PA6 to be an input pin, so that's why there's a 1 here. Now, inside my while loop, I'm going to read digital input and I'm going to write digital, or I'm going to use read commands to read in a digital input on my input pin, and I'm going to use write commands to toggle a 1 or a 0 on my digital output pins. And so if I want to read an input, I use the in special function register. And so if we go back here, sure enough, there is an in special function register. And if I click on it, it says the bit field shows the state of the port X pins when the digital input buffer is enabled. And it talks about what happens when you write to the input port, and usually you shouldn't do that. So this is just kind of an error case. Oops. Here's all of my reminders. And so basically this input, you just read from it. And so we've configured pin 6 as an input. If the voltage is low on pin 6, this will be a 0. If it's high on pin 6, the value of this register will be 1. There's also an output special function register. And this output register is meant to be written to. So if we write a 0 to a bit to PA5, here we will have 0 volts at our pin, and if we write a 1 here, we will have 5 volts at our output pin. And so this is super, super important. So this last little sequence that I've shown you here, this is how we make the connection between what we're doing in our program and what is actually happening on our printed or on our breadboard with all of our voltage levels, right? So, and this is what I mean by spending a lot of time reading the data sheet. Every single time you write a line in every single time you write a line in the in this file, it's basically going to be manipulating one of these special function registers, either reading something from it or writing to it. And the only way you understand which special function register to use and what values to write or what it means when you read from it is by reading the descriptions in the data sheet. Okay, so the last thing to do is just to check and make sure if we can program our chip. So we do that by, and my button's hidden. It might not be on your screen just because I've squashed my window here a little bit. But this is the make and program device main project. So make sure you've got video demo set as, or make sure you've got your current project set as your main project. So you just right click on this and set as main project. And then you hit this button and look at your output down here. So it's saying connected to programmer. And then you get a bunch of messages here connecting to MPLAB Snap. And then you get, different sort of version information. You'll get this only config settings that have been explicitly declared will be programmed. That's fine. You don't have to worry about that. Erasing. And what you're looking for is programming / verify complete. If you get this, you're done part A. Everything has worked. And you might say, oh, well, nothing's happening on my printed circuit or on my breadboard. How do I know that this actually works? Well, the Snap programmer is actively communicating with your chip during this programming operation. So there's two-way communication. It's sending messages to the AVR. The AVR is sending messages back to it. And you'll only get to programming / verify complete if, number one, your voltage levels are properly connected, right? So if the chip isn't powered up, you're not gonna get this message. And number two, all of your connections, with the Snap programmer are proper, and you've properly done the pull-up resistor. So all of these things have to be in place for you to get to this point. Now, it's possible that some of you might not get to this point. You might see an error in this window. And if you see an error, do not proceed with the rest of your lab. You have to fix your error. And like I said, there's some sort of typical errors at the top of the lab handout here. Target power not detected. You'll get that if you haven't plugged your programmer into VDD and ground. PDI physical timed out. You get this most often if your UPDI connection is not good between your programmer, or if your chip isn't properly pressed into your breadboard. Framing error, for me anyways, this came up most commonly when I didn't have the pull-up resistor connected properly. So these last two errors are usually related to your UPDI connection, the seating of your chip on the breadboard, or if your pull-up resistor isn't proper. So if you have any of these problems, if this is during the studio session, put up your hand. If you're doing this outside of the studio session, post on the discussion board. So anyway, this was a bit of a long video, but I wanted to go nice and slow just to make sure that I really sort of covered off all of the points that you needed to be careful of. Again, I hope going through this will set you up for success for the rest of the labs. And once you've finished lab 1, labs 2 and 3, I'm not going to be doing video demos, but it'll be definitely building on what you've learned in lab 1. So anyways, I look forward to seeing you in the lab and watching you get all this stuff working.